All right, let's dive right in. We're going to tackle a massive question today, one that sits right at the heart of, well, everything in computer science. How can we possibly create one single, universal language to describe what any program is actually doing? So here's the thing. How do you create one shared language to describe computation itself? I mean, a way to talk about what any system is doing, whether it's a tiny bit of code or a massive, complex AI. It sounds kind of impossible, right? But what if I told you the key to solving it might be hiding on a simple game board?
Yep, you heard me, chess. We're going to use the simple, familiar rules of a chessboard to understand a super powerful concept that underpins modern computation. Seriously, stick with me because this analogy is going to make everything just click.
Okay, so the big fancy term we're exploring is the algebra of states. I know, it sounds super academic and complicated, but for now, just think of it as the chessboard itself, the complete layout and the entire rulebook. It's everything you need to know before anyone even makes a single move.
So here's the crucial point. Any computational system really needs two things. First, you need that algebra of states. That's the what. It's the static setup, the board, the pieces, and all their possible positions. And second, you need the laws of motion. That's the how. These are the dynamic rules that tell you how a knight or a pawn can actually move around. The what and the how.
So let's look a little closer at that first ingredient, the algebra of states. Think of this as the unchanging foundation, the layout of the board and the, you could say, grammar of the game itself.
And this is where we really connect the dots. You see these formal terms? Let's break them down. The monad, don't let it scare you. It's just the grammar of the system, the board and all the possible positions for the pieces. And structural congruence, that just means that some differences simply don't matter. A knight is a knight, right? It doesn't matter if it's facing left or right on its square. It's the same piece in the same position.
Okay, so we've got our board and our pieces all set up. Now we need the rules of the game, the laws that tell us how these states can actually change from one to another.
And here's the key connection. These laws of motion are basically just rewrite rules. In other words, the rules for how a piece can move only make sense because of the board structure. The rules totally depend on the layout. You can't have one without the other.
And these rules can be incredibly specific. There's a formal term for this, one-hold contexts. But all it really means is that the system can target one specific location to apply a rule. Just like when you're playing chess, you focus on a single piece on the board to figure out your next move.
So that's the theory. But let's look at a real-world example. There's a language called Meta that actually puts this whole algebra of states idea into practice with a pretty clever system.
And you'll see our chess analogy holds up perfectly here. Meta has an input register. That's like making your opening move. It has a knowledge base. That's your book of grandmaster strategies. The workspace is the active game board where all the calculations are happening. And finally, the output is where the results go, kind of like the box where you put the captured pieces.
But, for a modern, decentralized system, those four parts aren't quite enough. It turns out there's one more crucial piece to this puzzle.
Meta adds a fifth component, and it's all about security. It tracks something called effort objects to manage how much a computation costs. And this is super important for preventing things like denial of service attacks, where someone could try to overwhelm the network with really expensive calculations. This system basically keeps things fair and secure for everyone. So, okay, we have this incredibly structured, formal system built on the algebra of states. But so what? Why go through all this trouble of defining computation so rigorously? What's the big payoff here?
Because this formal structure, the strict rulebook for how computation works, it unlocks a capability that is usually incredibly difficult, if not downright impossible, to achieve in programming.
It allows for something called BIS simulation. And yeah, it's another fancy word, but it stands for a really powerful idea. It's a rigorous, mathematical way to prove that a program is correct. It lets you demonstrate, with certainty, that your code does exactly what you designed it to do without any weird, unexpected side effects.
Let's bring it back to our chess analogy one last time. Having this formal system is like being able to prove, with mathematical certainty, that your opening chess strategy is guaranteed to lead to a checkmate. It's not just about hoping your program works, it's about proving it.
And that leaves us with a pretty fascinating final thought. If we can build our systems on a shared language that we can actually prove is correct, could this be the foundation we need to create truly transparent and trustworthy AI? It's a powerful question to think about as we move forward. Thanks for watching.